Ready, sir?
Okay, ready.
Start.
Good morning. Welcome to webinar classes TRE Society Hyderabad. This is physics class for senior inter.
बदकार है उसके किसी से ताल्लुकात हैं या किसी
Wave
तरह की कोई
optics.
ऐसी अखलाकी कमजोरी का पता चला कि उसकी बीवी से किसी और के साथ ताल्लुकात है, वो क्या करे? उसको तलाक दे सकता है, क्या कर सकता है? तो देखिए कि
Disturbance.
किसी भी शख्स को पता चला शादी के बाद कि उसकी बीवी का किसी और से भी कोई ताल्लुक है, तो उसके सामने दो रास्ता है, दोनों उसके लिए जायज है।
Sir,
पहला रास्ता
disturbance.
है कि वो तलाक दे सकता है, इसमें कोई हर्ज की बात नहीं, उसका ये हक है कि वो उसे तलाक दे सकता है, क्योंकि ये शौहर और मियाँ बीवी के बीच में
Sir, disturbance is coming.
अक़्द होता है, जो निकाह होता है, और उसमें सबसे बड़ी जिम्मेदारी ये होती है कि वो दोनों एक दूसरे के लिए होते हैं और एक दूसरे की इज्जत का ख्याल रखते हैं। खासतौर से बीवी का मामला ये है कि वो उसके लिए कोई दूसरा कोई ऑप्शन ही नहीं है, ना जायज ना नाजायज।
Sir, disturbance
शौहर
is
के अलावा
coming,
उसके
sir.
लिए कोई और ऑप्शन नहीं है कि किसी और मर्द से कोई ऐसा ताल्लुक करे। ना शौहर के लिए तो ऑप्शन है, एक जायज ऑप्शन है, दूसरी शादी कर सकता है, तीसरी कर सकता है, लेकिन नाजायज ताल्लुकात कोई नहीं बना सकता है, ना शौहर ना बीवी। तो शादी के बाद अगर शौहर को लगे कि उसकी बीवी के नाजायज ताल्लुकात है किसी से, या बीवी को लगे कि उसके शौहर के नाजायज ताल्लुकात है किसी के, शौहर अगर शादी किया है दूसरी कर ला तो कोई मसला नहीं, लेकिन उसके नाजायज ताल्लुकात है तो
Okay, sir. A disturbance is coming, sir. That's why I stopped.
Sir.
Okay. I will disturbance వచ్చింది అందుకోసం ఆపాను. Okay, I will start now. Good morning and welcome to webinar class. On wave optics we are discussing. And in the last class we have discussing Young's double slit experiment, and also we are seeing bandwidth or fringe width equation. The light waves coming out from two independent sources of light will not have any fixed phase. It has incoherent. There are two types of light waves we have discussed: coherent and incoherent waves. These incoherent waves means there is no phase constant with respect to time, but these cannot produce interference fringes pattern on the screen. So we want coherent waves to produce interference fringes. So Thomas Young take a technique to produce coherent waves. Coherent waves means the phase difference is constant with respect to time. So he used an ingenious technique to produce two coherent light sources with a constant phase difference between two sources. Even though you are using two same light sources, it is not possible. He used two constant phase difference between the two sources, light sources he used. How did he produce these coherent light sources? He used two pinholes S1 and S2 very close to each other to opaque screen. There are illumination by another pinhole that was lit by a bright source, illuminated by a bright source. Thus, the two sources through the pinholes S1 and S2, two light waves will generate. These two light waves are coherent sources. So, how these two coherent sources S1 and S2 are producing here interference fringes on the screen placed at a distance d. That screen is PQ. You can see a convex lens is also used from the source to produce parallel beam of light falling on S1 and S2. And S1 produces spherical wavefronts. According to wave theory, we are going to discuss interference fringes. So these produces crests and troughs like transverse waves, and these waves, spherical waves, are moving forward, and at the same time S2 also produces spherical waves. Those are also secondary waves and primary waves. And to understand it, we are taking crests and troughs as in transverse wave. Those are represented by dotted line and dark line. The dotted line is trough and dark line is called crest. So here on the screen PQ, you can see alternatively minimum and maximum points we are observing here. Where it is minimum points are shown in this diagram, red dots. These red dots, if you are observed carefully, one crest and another trough, when these two are joining by the superimposition of these two waves, we are getting minimum intensity. Then it is dark fringe is formed on the screen. To understand it, I have shown fringes also here with equal width. All the dark and bright fringes are same equal widths. And where you can see bright fringe, the bright band is formed when there are two crests or two troughs are combining. You see those are represented in blue dots in the diagram. So like this, on the screen alternatively, dark and bright fringes are formed on the screen. These are called interference fringes. Now, how to find out the fringe width? What is the length of the fringe width, whether it is white or dark? Here you see this is geometrical representation of the same experimental setup. S1 and S2 are separated by distance d, and capital D is represented the distance from source to the screen. And here on the screen, we have selected a point P. Any point at the center, both these two are combining. There is no phase difference between these two. The distance at the center of the screen O, S1O and S2O distance is same. We call it as path difference. Path difference between S1O and S2O is equal to 0. Why? Because exactly O point is equidistant from S1 and S2. Therefore, when the path difference is 0, we can see in the previous we have discussed about this. If path difference is exactly 0, then we can see a bright fringe. Therefore, at the center we can see a bright fringe, and alternatively we can see according to based on the path difference whether it may be bright or dark fringes are formed on the screen. Now coming to the point, a P point is shown in this diagram. At this point P, S1P and S2P, this is the path traveled by the waves, spherical waves from S1 and S2 and superimposed at P point. Then what is the path difference? Here you can take NQ or S2N. That is the path difference actually. S1P, S2P is greater than S1P. So S2P minus S1P, which you can give NS2. That is the path difference we have to find out. Here you can see a triangle S1, S2, N is a right angle triangle. In this right angle triangle, we can find this Sn value. Like this, we can find out the path difference. By that, whether at P point maybe, at this P point may be bright fringe or dark fringe may be formed. Let us see the spherical wavefronts emanating from S1 and S2 produce interference fringes of bright and dark equally spaced on the screen, placed at a distance d from the slit. The bright fringe corresponds to a point on the screen due to constructive interference. We have already discussed about constructive and destructive interference. When two coherent waves are superimposed each other, sometimes constructive interference takes place. Then the path difference, S1p difference S2p, which is equal to n lambda. It becomes n is 0, 1, 2, 3, 4, or whatever it may be. You can see a constructive interference. Similarly, the dark fringe corresponds to a point P on the screen due to destructive interference. That path difference, S1p difference S2p, which is equal to what you have to take lambda, odd number of lambda, 2n plus 1 or n plus half lambda. And again, n is equal to 0, 1, 2, 3, and so on. So now see this diagram carefully. What we have drawn the same geometrical diagram, S2p square minus S1p square. That is, we are going to see path difference, therefore squares of this according to that geometry, that is a right angle triangle. From that OP distance is taken here as x, and S1, S2 is taken as d, small d. So in the right angle triangle, you are taking S2p means d square plus x plus d by 2. If you construct a right angle triangle with P, S2 and a point here below O, you have to take one point that is not shown here. So in this right angle triangle, you can take S2p is the hypotenuse. Therefore, S2p is written as d square plus x plus the remaining d below the O length is d by 2. So x plus d by 2 whole square, that is S2p square, minus what about S1p? Here also you can construct a right angle triangle. From that easily you can understand half of the x you can see. So minus d square plus x minus d by 2. The length here OP is x, and remaining length what it is means x minus d by 2. So that is square. While simplifying, you can get this is 2xd. So this is S2p square minus S1p square means a square minus b square form. You can write a plus b into a minus b. So S2p minus S1p is equal to 2xt by S2p plus S1p. We are dividing that one. So x and d are very small compared to d. Here x and d we have taken, we are some approximations we have taken. That is S2p plus S1p approximately taken as d plus d. Actually, it is not exactly d plus d. Approximately we have taken that. That's why x and d are very small. We have taken that is 2d. Similarly, then what happens for the above S2p minus S1p? That is 2xt by 2d. Instead of S2p plus S1p, we are taken as 2d. So what is S2p minus X1p? 2 get cancelled out, xt by d, or x is equal to, x is given as S2p minus S1p by d by d. Condition for this x from O to P point distance that we have taken here. Condition for bright band is S2p minus S1p. This is path difference. Path difference should be n lambda. Path difference should be n lambda. For example, there are n bright bands or nth bright band we are observing from this distance screen xn. Nth bright band is there. Then what is this path difference? That is equal to, according to above formula, n lambda d by d, where x you have to take as path difference is substituted n lambda here, n lambda d by d. X is S2p minus S1p into d by lambda. S2p minus S1p, this path difference for bright band is n lambda. Therefore, substituting n lambda in that, x you can get. What is the length of OP? For example, nth band is at P. So how to find out this distance means you have to substitute x. So n lambda d by d. Similarly, nth dark band is given. If, for example, it is dark band is formed there, then how to write xn? That is n plus half lambda d by d. Bright and dark fringes are equally spaced. This is most important in case of interference. Coherent interference produces equal width of bright and dark fringes. So the distance between two consecutive bright or dark fringes is called fringe width. It is represented by beta. So consecutive length on the screen, x n plus 1, what does it mean? N plus 1th brightest fringe minus xn, nth brightest fringe. For example, 7th bright fringe and 6th bright fringe. Difference of these two, you can get the width of the each bright fringe. So subtracting these two, here we have to take in the above values, n plus 1 minus n. xn is n lambda d 2. So n get cancelled, lambda d by d. Here we can get, this is the expression for fringe width, where lambda is wavelength and d is the distance between slits and the screen, and small d is the distance between two coherent sources, S1 and S2. You should remember this formula. This is very, very important. So the bandwidth depends on two important factors. From this equation, you can tell. First one is lambda, wavelength of the source which we are using, S1 and S2 wavelength. And D is distance from the source to screen. And small d is distance between the two sources. So now let us see another phenomena. We are already discussed reflection, refraction, and interference, and fringe width. All these, starting from wave theory, we are discussed the some properties of light. This is also one property of light, diffraction. If we look clearly at the shadow cast by an opaque object close to the region, geometrical shadow. For example, you take an opaque object and incident light with a torchlight on this object, you can see the shadow of the object. Then if you closely observe the shadow is not sharp. This shadow, you can see some dark and bright fringes, just like dark and bright regions. Here we should not tell the word exact fringes. It is only regions. Dark and bright regions are formed, as in case of interference. In general, in daily life, where you can observe this diffraction, I can give 2 examples. If you see compared to the CDs, nowadays all of you see that CDs, the color of the CD, what is it? If you see it, different colors you can see. This is due to diffraction. Another one, the shade of any object, object shadow at the edges, sharp edges, you can see the diffraction, bright and dark regions. The above 2 examples, phenomena of diffraction. As the wavelength of light is very, very small, we have already known it, than the dimensions of obstacles. When you compare the dimensions, length, breadth, and all these of the object which you are placing in the path of the light, those dimensions are very high when compared to wavelength, that is micrometers and nanometers. You know, the visible light itself, 0.4 micrometer to 0.7 micrometers of wavelength. The remaining we cannot see. Why? The reason is very, very less or very, very high. So if the wavelength is very, very small when compared to the object dimensions, we cannot encounter the diffraction effects of light in all the cases. Particularly, if you are interested and you have to use separate instruments, then only you can observe. Now, what is diffraction? According to definition, it is a phenomena of bending of light around the sharp corners of an obstacle placed in the path of light is called diffraction. Here, bending of light is, we have already discussed it, is refraction. Is there any difference between refraction and diffraction? Refraction means entering the light into the medium and comes out again. This is a refraction. But here, this is also bending, but the bending is very, very, very small as compared to that of refraction. You can measure refracted angle and incident angle. You can find the refractive index of the material also. But here the important thing is diffraction takes place in certain conditions only. The main condition is the object dimensions. There are two diffractions you can observe. When you are placing an object in place of light wave, at the edges you can observe. So due to obstacle, you can observe diffraction. And second thing, without this obstacle, experimentally, if you are a pinhole, as you have taken interference, you have taken S1 and S2, like that you have taken only one slit, single slit, a small hole, and light is coming from that hole, then you can observe at the hole, the light waves bends. Initially, they will travel in straight line. At the edges of the hole, if this slit is very small, then you can observe this diffraction. Experimentally, we have to take the single slit method. Now, let us see how this diffraction, you can see the examples what we have taken. Diffraction of light takes place when the aperture of slit is comparable. That is most important. The aperture means its length. Length and breadth, if you are considered as rectangular aperture, thus length should be very, very small, comparable to the wavelength of incident light. That is one thing. Second thing is, it can be observed when the dimensions of the obstacle are comparable. We have already discussed about this. These two conditions, then only you can see diffraction. This diffraction also explained by using Huygens wave theory. Here you see light diffraction by blade. Light is formed on the blade. The edges of the blade, you can see some shadows. Why? The reason of these shadows are due to diffraction. Here you see the edge of the blade is very, very sharp, comparable to the wavelength of incident light. That's why you can see like this, exactly the edge of the blade is not observed. Where is the edge? You goes on from this edge, you can see dark and bright line. Similarly, I have discussed about a disc, CD disc, compact disc, you can see like this different colors due to diffraction. Okay, so this can be also explained with the help of diffraction. So here you see, here also diffraction takes place when a wavefront is partially obstructed, only the wavelets from the exposed parts superimposed and produce diffraction pattern of bright and dark fringes. The most important thing you have to understand is the main difference between diffraction and interference, which we have already discussed. Is here, in case of interference, there are two light waves are necessary. Superimposition of two or more. The coherent waves should be, wavefront should be superimposed and form interference pattern. But in case of diffraction, due to superimposition of same wavefront, only single light will come, but due to the edges, while it is traveling through the small holes, then it takes a bending. And due to this bending of these wavefronts, same wavefront, we can see alternative bright and dark fringes. And another important difference is the width is not equal in case of diffraction. bright and dark fringes width is exactly equal in the pattern of interference. But in case of diffraction, the bandwidth, whether it is bright or dark, it is not exactly equal. Unequal width of white and dark fringes are formed. That is most important. Now let us see diffraction pattern for a single slit. What we have discussed, a single slit is formed here. Ln is the slit length, and breadth. The rectangular slit is taken, and here a parallel beam of light is falling on this slit. While wavefronts are observed, a wavefront will come from left side to this Ln, and only the Ln part, the wave will move to forward. There are two dots, M1, M2, M1 and M2, and also M. M is the dot exactly at the center of Ln, and M1 and M2 are again two dots between the centers of Lm and Mn. Why we are taking these dots means, according to Huygens wave theory, every point on the primary wavelet, Ln is the now primary wave comes out from this slit. Therefore, on this we have taken different points, and each and every point acts as secondary wavefront. Therefore, when a parallel beam of light is incident normally on a single slit Ln, its width is small a. The diffracted light goes on to meet on the screen. Here, the screen is not shown here. There is a screen 2.2 P, 2 point C. There are 2 points I have shown here. A straight line through M, perpendicular through slit, meets the screen at C. Exactly at the center of Ln, a light rays goes to the C point, and intensity is also very high. Why? Because complete superimposition of waves are formed here. Red color waves we are shown here. These are blue color. Blue color means direct rays, and these red color light are diffracted light. Taken some angle. Not only you can see the light along the parallel beam of Ln, it can see upwards. They are taking some diffracted angle theta to meet the P point. Let us consider a point P on the screen which collects the waves from different points on the slit. Actually, there also you can use a convex lens also, and we have source is monochromatic light. Here we have taken source from S. The monochromatic light comes from it. At C, diffraction increases. The angle of diffraction at C is 0. The point P will be maximum intensity depending on the path difference. While we are going to discuss about this, at the central point P on the screen, the angle theta is 0. The path differences are also 0. Hence, all parts of the slit contribute in phase. It is exactly same phase. This gives maximum intensity. This is central maxima. This is known as central maxima. The path difference between two edges L and N of the slit. Let us take at the edges L and N. The path difference is at P point NP minus LP. If you observe the diagram, that is NQ, we have taken slit length as hypotenuse on side, and you can write the sin theta value. Then sin theta is NQ by A. You can get LNQ. LNQ in the triangle you observe. Then once you see that now what is the theta is very small, you can take sin theta place, you can replace it as theta. So the path difference is A theta. What is A? A means distance between the 2 points on the slit, L and N. This length is taken as small a into theta. the angle of diffraction. Divide the slip into two equal halves. Now you consider whether according to this theta value, whether here forming exactly a P at this P point, whether exactly intensity is 0 or not, we cannot tell. That's why you can take a different values, divide the slit into two equal halves by taking M point, LM and MN. What is this length? This is A by 2. The path difference between the waves sent by 2 points on the slit separated by A by 2 is A into theta by 2. You can understand, I think, that the path difference, distance between the points, that is A by 2, angle is theta. Therefore, A theta by 2. The path difference is, if the path difference is lambda by 2, what happens? A theta by 2, which is equal to this path difference is, once you consider lambda, it is bright. If it is lambda by 2, what happens? Theta is equal to what happens from this lambda by A. So the path difference of lambda by 2 offers a phase difference of pi, you know it. Hence, the two waves will cancel each other and form minimum. When path difference is pi, it is called destructive interference. Two spherical waves participate in destructive interference, cancel each other. Then what is the condition at P with 0 intensity? Means dark region is observed at P. So the condition for minima is theta is n lambda by A, that is n is equal to, n is plus or minus 1 plus or minus 2. Both sides, the same condition, half of the screen, we are observing that above the LM and below the MN, below the LM part, the same conditions you can observe. From the central maxima, both sides, brightest and other maxima become weaker and weaker. Again, this continues, this process, sometimes constructive interference and sometimes destructive interference formed on the screen. While increasing n, here n lambda by A, we are writing formula. First one, second one, third, fourth, fifth, condition going on. What happens? Waves from it, its intensity decreases. Now you can see from this graph, the following is the graph drawn between intensity and angle of inclination, diffraction, for the diffraction pattern of a single slit. You observe this diffraction angle, lambda by A, 2 lambda by A, 3 lambda by A. Intensity at the center, you can see maximum intensity. At point O, you can see that left side, negative direction, half of the width is divided into two parts. And screen, you can see like this, high intensity, bright fringes, and again suddenly decrease in the brightness, you can observe here. So this is a pattern of diffraction angle and intensity of light in a single slit. Now you have to remember the important things. It is a diffraction is a general characteristic exhibited by all types of waves. That is most important. What type of waves? Sound waves also diffracts, light waves, water waves, matter waves, longitudinal and transverse, mechanical waves, which we have already discussed. Mechanical waves again, longitudinal and transverse. Both longitudinal and transverse waves participate in diffraction. You should remember that. In what is the main difference? Here we have already discussed the differences also. And in interference and diffraction light energy, both cases, the light energy is redistributed. Bright and dark fringes are formed in interference as well as in diffraction. In these two cases, light energy is distributed. If it reduces in dark fringe, light energy is reduced at dark fringe. At the same time, it increases at a bright fringe. So totally, the sum of the energy of light is constant. There is no gain or no loss of energy, which consistent with the principle of conservation of energy. This we have to conclude diffraction. Actually, there are two types of diffractions also there: Fraunhofer diffraction, Fresnel diffraction. The main difference in Fraunhofer diffraction, the source and screen are infinite distances. We cannot fix the source and also screen. When light is entering into sunlight, entering into a dark room with a very slit, the window is open very just like a slit. You can observe these fringes. So you are not putting this sun that is already there. What is the distance of sun? Infinite distance. So you are not placing the screen on the wall. You can see these lines. So this is Fraunhofer diffraction. In Fresnel diffraction, the source and also screen, both these two are finite distances. That is the only main difference. No lenses are required to see Fresnel diffraction. But
conclude, sir.
The theoretical treatment is complex. That's why we are not going to detail about that. So this ends the chapter. You should remember this is also a short answer notes question: diffraction and interference. But Huygens wave theory is very important. I think you can understand the wave theory, how we can explain these different phenomena of light. Thank you very much. Let us conclude this lesson today. Thank you all.